Let's continue our talk of resistance. First of all, when resistance occurs, you have to have energy to overcome that resistance. And there's the concept of joule heat. The joule heat is the energy that's used that overcomes resistance and is converted into heat. If it's energy, energy can always be converted into heat or expressed in another way. So joule heat is the energy in the heat value that is used or is required to overcome the resistance in a particular conductor. So here we have a conductor, and we want to measure or look at the properties of that conductor which cause resistance. First of all, the length of the conductor, L, the longer the conductor is, the more resistance that would be encountered. Secondly, the material itself, whatever it's made of, would also increase the resistance. So those two factors, the length and the resistivity, or the property of the material itself, those two would be directly related to the resistance. So as each of those goes up, the resistance would go up. Alternatively, however, the cross-sectional area would decrease the resistance as it got larger. If you think again in terms of a flow of water or something like that, the more area that you have to move through, the less resistance you would see. And that's also true for electrons. And so what you see here is a formula that can be put together that relates resistance to the resistivity, that is the material itself, times its length divided by the cross-sectional area. So the most important factor is the material's resistivity, but also the diameter or cross-sectional area of the conductor, as well as the temperature. That's something that's not considered in this formula. And then the length of the conductor. So the temperature is actually not listed here, but it is also something that would make sense that if you have more internal motion, there would be the potential of either increasing or decreasing the ability for a material to conduct. So let's talk about one of the more important laws in electrical current, and that is Ohm's law. As I said before, a superconductor is a material that would allow electrical flow without resistance. The problem with developing a superconductor has been they've only been developed at temperatures close to absolute zero, which are not practical in use in general situations. Ohm's law states that the current that flows through a conductor is directly proportional to the voltage and inversely proportional to the resistance. And it looks like this. The voltage is equal to the amperage, or the current, times the resistance. And so here on the left, you have this formula. If you know the voltage and you know the amperage, then E divided by I equals R. I times R is equal to E, and then E divided by R is equal to I. So this is one way, and we use this kind of triangle, if you remember, with density, where density was where volts is, and the mass was where the current is, and the volume is where the resistance is. And so density was where the current is, and volume was where the resistance is, and mass was where the voltage is. So mass over volume is equal to density, and so forth. Well, this is a very similar way to remember the relationship between voltage, amperage, and resistance. I times R is equal to E. E over I is equal to R. E over R is equal to I. Similarly, you can set up a similar triangle with voltage times amperage in relationship to power. Power is equal to voltage times amperage. voltage is equal to power divided by current, and amperage is equal to power divided by voltage. So these two circles, you can use these to help remember the formulas that we'll be using on quiz or test in relationship to this material. So let's take a look at a couple problems here. Calculate the voltage difference in a circuit with a resistance of 35 ohms and a current of 0.75 amps. So let's take a look at this. If we draw our little circle, we put E up here, I over here, and R over here. That just helps us remember. So that means we want to calculate the voltage. So E is equal to IR. And so that's going to be equal to 35.0 times 0.75. That's equal to 26.3 volts to 3 significant figures. Let's take a look at the second one. A toy car with a resistance of 35 ohms is connected to a 12-volt battery. How much current flows in the car? Let's draw a little circle again. E, I, R. Now in this case we want to know I. So I is equal to E over R. So we have a 35 ohms is in the denominator, and a 6-volt battery is in the numerator. And so 6 divided by 35 is going to equal 0.171 to 3 significant figures amps. Now let's take a look at circuits. We're going to finish up this week by taking a look at circuits. And there are 2 types of circuits that we have to take a look at. An electrical circuit is the path that the electrons or the electrical current flows, and it's composed of a source, which is the battery, a conductor, which is the wire, and a load, which is a device that transforms the electrical energy into some other form of energy, such as light energy or heat energy or mechanical energy. A closed circuit is a circuit that has its pathway complete so the electrons can flow. Now, I'll explain these terms in more detail in the next few slides, but on the left is a series circuit, and on the right is a parallel circuit. Now, an open circuit is when the electrical path is open such that there's a section where the electrons can't cross, and this is shown on the left. You see that those 2 wires are disconnected such that it cannot cross, and therefore you have no flow. That's how you turn off a light, is you break the circuit. A switch is a device that will either open or close the circuit, and that's what's shown here on the left. Is an open circuit, and a switch that will either open or close the circuit. Now on the right here is what's called a short circuit. A short circuit is a situation where the electrons can take a shortcut, in this case skipping the light bulb, and derail or cause a problem with the electrical circuit. Now the best case scenario is that the light just doesn't work. But sometimes electrons will run into each other going in opposite directions, and a great deal of heat is generated, and it can cause heat and subsequently a fire. So in order to prevent this from happening, we have certain things called fuses. And this is an example of a simple fuse. A fuse is a narrow strip of metal that is fragile and has a very low load ability, and if it's overloaded, it will break the circuit and prevent electrical accidents. So a circuit breaker, what we call a circuit breaker, is just a more complicated automatic switch that functions as a fuse. And if you look at this, actually this whole diagram, it's kind of hard to point out the circuit breaker in here, but there in this relays, there are what they are talking is a 180 amp relay. That is actually a type of circuit breaker in which if it goes over 150 amp on this one and 180 on another, it will automatically switch off and stop the electrical flow. And these circuit breakers are what we have in our homes in the circuit boxes when you go down and you flip a switch on and then off. Now, I said there were two types of circuits, series circuits and parallel circuits. A series circuit is where the loads are lined up sequentially, which means in a single line, like this. This is an example of a series circuit. This is the way a series circuit is drawn in a schematic. The battery or the source of electrical power is shown on the left, and then the three resistances are shown as jaggedy lines, and this is just a standard way in which to write this. These two diagrams essentially show you the same thing. A circuit that in a series circuit, the current remains constant. So the current at the battery, the current at the first resistance, the current at the second resistance, the current at the third resistance, and back to the battery. Anywhere you check the current in this, it's always going to be the same. That's an important thing to remember. The resistance, the total resistance in a circuit, is the sum of the three resistances, or however many resistances there are. So the total equivalent resistance, or RT, is equal to R1 plus R2 plus R3. The voltage is summed, so that if you measure the voltage at R1 and at R2 and at R3, if you add those three voltages together, you get the total voltage that would be produced at the battery. So the resistances are summed and the voltages are summed. And remember, at each resistance, V is equal to IR. V is equal to IR2. V3 is equal to IR3, and so forth. So Ohm's law applies throughout the circuit. Now, a parallel circuit is set up in such a way as that each load is separate and isolated so that it can operate on its own. One of the disadvantages of the series circuit is if one of these three lights burns out, then the whole circuit is shut off. And some of you all may have electrical lights on your Christmas tree that are like this, where you have to go through and try to find which bulb is burned out, and you can't get any of them to work until you find the right one. Parallel circuits, on the other hand, this doesn't happen. So here's what a parallel circuit looks like, and you can see that if one of the light bulbs burns out, the other two are still free to operate. And this is how it's drawn schematically. So the voltage, unlike the difference between a parallel and a series circuit, is in a series circuit the amperage is constant. In a parallel circuit, the voltage is constant. The resistance, the equivalent resistance, is calculated using this formula. 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so forth. And then lastly, the total current is the sum of the current measured at each load. Again, Ohm's law works at each site. So let's take a look at a couple of problems now. We'll finish up looking at a couple of problems related to series and parallel circuits. So here is a series circuit, a 9-volt battery with 3 resistances in series of each of the following values. What is the equivalent resistance? Now that means what is the total resistance in the circuit. So in order to do that, we have to remember that the total resistance is equal to the sum of the individual resistances. So the equivalent or total resistance in a series circuit is equal to the sum of the three resistances that are shown here, which is going to be 100 plus 300 plus 50, or 450 ohms. So if we took these three out and put one resistance in that was equivalent throughout, then it would be a 450 ohm resistance. What is the current? Well, remember that Ohm's law applies. So E is going to equal IR. We want to know the current, so that's going to be equal to E over R, and R here has to be the equivalent of this 450. And so we have a 9-volt battery divided by 450 ohms. So a 9-volt battery, if we take 9 divided by 450, we're going to get the answer of 0.02 amps. What is the voltage drop across each resistor? Now what that means is how much voltage is used to get through this resistance, how much of the energy is used here, and how much of the energy is used here. In every case, the voltage is going to be equal to IR. So at the voltage drop at the first resistance is going to equal the amperage, which is constant throughout, 0.02, times that first resistance, which is 100. So the voltage drop here is 2 volts. At the second one, it's going to be 0.02 times 300, which is going to be 6 volts. And then the last one is going to be 0.02 times 50, which is going to be 1 volt. And this sum of these three has to equal the total, which is 9. And the good thing is that it was equal to 9. Now let's take a look at the second problem, which is a parallel circuit. You have the same 9 volts. Now you have 3 resistances in parallel. And it says, what is the equivalent resistance? Well, remember that the equivalent resistance, 1 over the equivalent resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3, which is going to be 1 over 90 plus 1 over 45 plus 1 over 180. And there's a couple ways you can do this. One is you could find the least common denominator here, which looks like it might be 180. And so 90, that's going to be 2. This is going to be 6. And no, that's not right. How about 4? This is 4. And this is going to be 1. So if you add those three up, you get 7 over 180 is equal to 1 over RT. So that means that RT is 180 divided by 7. So if we take 180 and divide that by 7, the equivalent resistance here is going to equal 25. And really we only have one significant figure, so 25 is going to be the, well, let's say 26 ohms. It's actually 25.7. Let's say 26. Now, I would not put 30, okay? I would just say 26. What is the current? Okay, the current is constant throughout a parallel. I'm sorry. The equivalent current is going to obey Ohm's law. So E is IR. So I is equal to E over R, where R here has to be the total that we just calculated. So we have 9 volts and 26 ohms. So the overall current is going to equal 9 divided by 26, or 0.35 amps. 0.35 amps would be the equivalent. And then what is the voltage drop across each resistance? Okay, the voltage drop, there's no such thing as voltage drop. If you remember back here, the voltage is constant. So the voltage drop across each is equal to the voltage total is equal to the voltage drop. And so the voltage drop is going to be 9 volts. That's kind of a trick question. So what that means is that you'll have 9 volts here, 9 volts here, 9 volts here. So the flow through each of these is going to be different, but the sum has to equal this. And so if we take I1 would equal 9 divided by 90, or 0.1. If we take I at 2, that's going to be 45 divided by, 9 divided by 45, which is going to be 0.2. And I3 will be 9 divided by 180, which is going to be 0.05. If you add those three up, you get that.